All right, here we go. This is take one of the second video presentation for ME304. Let's go ahead and get started. In the beam system shown, values are as follows. A is equal to 12 inches. This here is 12 inches. B is equal to 6 inches. This here is equal to 6 inches. C is equal to 10 inches. This here is 10 inches. D is equal to 8 inches. Where is D? 8 inches. PX is equal to 100 pounds. PX is this here, PX. This is PZ. This is PY. PX is equal to 100 pounds. PY is equal to 175 pounds. PZ is equal to 125 pounds. So first thing we want to hold on. All three sections are find the principal stresses and the maximum shear stress at point H. Point H is there. All three sections are solid cylinders with diameter 1.5 inches. We're going to be using that for the area, the polar moment of inertia, etc. So let's go ahead and get started by drawing the free body diagram. Okay, so the free body diagram is going to look something like this. Okay, where we have this distance here, 12 inches, this distance here, 6 inches, this distance here, 10 inches, this distance, 8 inches. We also want to write the reaction axes. If you notice, here's the Y, Z, and the X is the longitudinal. I'll get to that in a second. So we have RY, reaction in the Y, reaction in the X, and reactions in the Z. Each one of these has moment reactions, which positively shown right here, moment in the Z, moment in the Y, moment in the X. We should draw our forces, which is red. So RY, which is right here, which was 175 pounds. Then we had PZ, which was 125, and PX, which is 100 pounds. So here's our free body diagram. Something important to point out about this free body diagram is that X is the longitudinal. This is important because it tells us where to look at the cut from and how the different forces will cause different reactions. Something we can't leave out is point H, which just sits right here. Cool. We now have our free body diagram. The next step is to find our reaction forces to these reaction forces and reaction moments to these loads. So for this, we will draw a cool table. We will have the R vector, which is just the position vector from the cut section. this will have components I, J, K. In some cases, we'll have a force vector for each one of the loads. These will also have I, J, and K vectors. Maybe. We have to check. And then the definition of moment is equal to R cross F, which is pretty important because to find our moment reactions or the moments caused by these loads, we're finding the loads caused, or the forces caused by these loads and the moments caused by these loads to find the reactions in the beam. So like we said, M, it's also going to have I, J, K components, which are going to be calculated from these two vectors. So let's go ahead and start off with the X vector, or I mean the X load, which is 100 pounds. The R, where is it located? So if we look here at our free body diagram, it is located 12 inches down the X, 6 more inches, that makes 18. So 18 inches down the X. And then 8 inches up the Y. And it's neither left nor, or I mean, it moves neither, it is positioned in neither direction on the Z axis. So this K component is 0. For the force, we see that it is completely in the X direction, so it's going to have a 100 pound component in the I, pound, and then 0 components in the J, 0 components in the K, because it's pointing down the longitudinal axis, which is the X axis. So when we cross these two vectors, I went ahead and did the math already. We're going to have 0, 0, minus 800 inch-pounds. So there's the first load. Let's move to the second load. We'll do the next two a bit more quickly. So we'll go on with the Z. So 175 pounds. The R vector for that is, it goes down 12 inches, then it goes in the Z 10 inches. So this is going to be 12, 0, 10, because it doesn't move in the Y at all. It's not positioned in the Y at all. The force is going to have 0. It's pointing down, so it's going to have a negative 175 pound J component and 0 Z components. When you cross these two vectors here, it leaves you with a moment vector of 1,750 inch-pounds, 0 in the J, and then in the Z you have a negative 2,100 inch-pound moment caused by this load. Moving on, the 125 pound load has an R vector of 12 plus 6 in the X, which is 18 again. Also it's going to have the same vector as the same position vector as the X load, as the PX load, 1880. The force though, it's going to be different because it's pointing in the negative Z direction and no other direction. So it's going to have 0 I component, 0 J component, negative 125 pounds in the Z component. Once you multiply these two vectors, it gives you a moment vector of minus 1,000 inch-pounds, 2,250 inch-pounds in the Y, and then 0 in the Z, or in the K, IJK, sorry. So now, to find the reactions, our next step is to find the reactions. We do this by, we're going to have force reactions and moment reactions. So our X, the reaction in the X, is going to be the opposite of this force. If they had multiple components, or if the different loads had multiple X components, we would sum them up. So since there is none, it's just minus 100, opposite of 100 pounds. RY, once again, it is simply the opposite of the sum of these, which is positive 175 pounds, and then RZ, once again, the sum of these, the opposite, so positive 125 pounds. Moving on to the moment reactions. Moment in the X is going to be equal to just the opposite of the sum of these. So if you sum these together, you get positive 750. So the reaction is going to be negative 750 inch-pounds. The reaction moment in the Y is going to be equal to the sum of 0 plus 0 plus 2250, which is positive 2250 inch-pounds. So the opposite of that is negative 2,250 inch-pounds. The moment reaction in the Z is going to be the sum of these, which gives you a minus 2,900 inch-pound. So the reaction is going to be positive. So positive 2,900 inch-pounds. We now have our reactions ready. Something else we can prepare, I guess. Or actually, we'll do that when we get there. I was gonna say we could prepare the surface area of the cut. We can also prepare the polar moment of inertia and the moment of inertia. But we could just do that when we get there. So let's go ahead and get started. So to find out the stress caused by Rx, it is in the longitudinal axis. So if it is in the longitudinal direction, if it is a force, it will cause axial stress. So Rx is going to be axial stress. So to analyze this, we need to analyze the cut. And when we're looking at an axial stress, we need to look from either lateral direction, so not the X. So let's say we look down the Z, that's going to give you H is here. So if we were looking on the other side of this, down the Z, this is what we would be looking at. So Ry would be here, and Rx would be here, and H would be there. So this would give you a axial stress in the X direction, which is equal to, or I'm sorry, we need to draw our reaction. So reaction in the X is in the minus X direction because it's minus 100. So this is positive X, this direction is negative X, and this is 100 pounds. And if you notice, it's pulling this way. So that means that it is in tension, which means we will have a positive stress, positive axial stress, plus the load over the area, which is equal to 100 pounds over the area, which we will now find, pi over 4 times the diameter squared. And this will get us an answer of 56.588 psi. Let's make sure that is true. So 100 divided by pi over 4 times 1.5 squared, 56.588, or 588 psi, pounds per square inch. Okay, that's our stress in the X caused by reaction X. So moving on, let's see what reaction Y causes. Ry is equal to, or Ry, it's in the lateral direction and it is a force. Therefore, I'm looking at my notes here. Lateral direction, if it's a force, it will cause transverse shear. So once again, we will analyze the cut. Okay, so view angles to look from. If it's transverse shear, we need to look from the lateral direction that the force does not act in. So the force acts in the Y. The other lateral direction is the Z. So we will be looking down the Z axis. Let's go ahead and draw what that would look like if we were looking down the Z axis. It's pretty much this. Once again, we have H here. Once again, we have RY, once again, RX. And we should draw the force, which is positive 175 pounds, which looks like this. So transverse shear, we know that transverse shear, so the plane that it's on, if we look at H up here, it's on the XZ plane. So this would be XZ is equal to VQ over IT, shear, first moment of inertia, and thickness. But it is going to be equal to 0 because Q is equal to 0 at the outermost fiber. You might be asking why is that the case? That is because Q is equal to Y bar prime times A prime. We'll see this later on. And A prime is the area past the cut, or past the point of interest. And if you notice, this is on the outermost fiber, so there is no area past the point of interest. This would go to 0, Q would go to 0, making it equal 0. So RY does not cause any transverse shear. Moving on. We've done RX, we've done RY, now on to RZ. So it is also a force in the lateral direction. Just like RY, it's going to cause transverse shear. So let's look at RZ. We will now be looking from, if you recall, the transverse direction the direction in which the force does not act, which we will be looking down the Y now in this case. Let me make sure, sorry. I hope that was all in the video. If not, here it is. So Q is equal to 0 because A is equal to 0, which means tau xz is equal to 0. Back to here. So, like we said, we need to look at the cut down the lateral direction in which the force does not act in. The force is acting in the Z, so we need to look down the Y, which means if we're looking down at this, because we're looking down the Y, so if we're looking down at it, H is here in the middle. This is H. Our axes are going to look like this. RZ, RX, the longitudinal. And then we need to draw the force, which is positive 125 pounds. So this is positive shear, which is important in the next step. So tau, once again, we already explained that H is on the XZ plane. So this would be XZ is equal to VQ over IT. T is the thickness, which is just the diameter. I we can find using the moment of inertia for a cylinder. V is shear, which is here. And Q, like we said, Q is equal to Y bar prime times A prime. So to find Q, we're going to need to look down or look at an end view n/cut u. So if we look at it, RZ is going to be here. RX here. And H will be here. Something important to note is the neutral axis. Okay. Okay, I explained that A prime is the area that is above the point of interest, which will be this entire area here. So this is A prime. I did not explain what Y bar prime is. Y bar prime is the distance from the neutral axis to the centroid of whatever shape is made by looking at the area above the point of interest. So the centroid of this hemisphere here. Y bar prime. So area is equal to pi r squared over 2. And then Y bar prime. Sorry, this should be A prime. Yeah. This is equal to the centroid of a hemisphere or semicircle. Well, I don't know why I call it hemisphere. So Y bar prime, this equation is 4r over 3 pi. And we should just plug in numbers to find these values now. So pi times radius is 1.5 over 2 inches squared over 2, which is equal to, this will move down here, equal to 4 times 1.5 over 2 inches squared over 3 pi, which is equal to, let's go ahead and do this in the calculator. So 1.5 over 2 squared times pi over 2, 0.88357, yeah, 0.8836 we'll call it, inches squared. And then Y bar prime, 1.5 over 2 squared times 4 over 3 pi, 2.356. Did I do something wrong? Let's recalculate. 1.5 over 2 squared times 4 times 4 over 3 pi, 2.356. Looks like something is off on my calculations. Let's make sure. 1.5 over 2 squared times 4 divided by 3 times pi. Aha. 0.238, which still doesn't look familiar, and I don't know why I'm getting a different number. Let's run it again. 1.5 over 2 squared times 4 divided by 3 times pi. 0.238. We'll run with that. 0.239. Y bar prime is in inches. Yeah, I swear. Oh, it's not squared. What am I thinking? Okay, caught the mistake. So now I'll go through and delete all of these. Okay. Okay. I just want to have the float for later calculations. So 1.5 over 2 times 4 over 3 pi. Oh geez. 1.5 over 2 times 4 over 3 pi. 3.14. Did I just get pi as an answer right now? This should not be the answer. 1.5 over 2. That is the radius. Times 4. Divided by 3 times pi. 0.318. This is what I'm rolling with because this is what my answer is. 0.318 inches. Cool. That took way too long. Sorry, Dr. Lehman. So now A prime times Y bar prime, which is equal to Q, is equal to 0.28125 inches cubed. And we can now continue to find actually find tau xz, which is equal to the shear, which is positive 125, pointing in the positive RZ. So 125 pounds multiplied by Q, which we found here, 0.28125 inches cubed over moment of inertia of a cylinder. Moment of inertia of a cylinder is pi over 4 r to the 4th, which we will replace r with 1.5 over 2 to the 4th. Yeah, sorry, that's kind of sloppy. We'll roll with it. 1.5 over 2 to the 4th times the thickness, which is just the diameter, I believe. Let me double check that. Yes. This is all equal to, let's find out, times 125 divided by 1.5 over 2 to the 4th times pi over 4 times 1.5. 94.314. 4.314 pounds per square inch. Cool. So now we can move on to the moments. Moment about X, what is that going to cause? So if it's a moment along the or on the longitudinal direction, it will cause torsion. So we're going to look at an end view, end/cut view. That's kind of bad circle, but that's okay. When we're looking at torsion, we look at the axis the moment is acting about, and it's acting about the X, so we're looking kind of through there, through the X, through the longitudinal. If that's the case, that means we have RY. I'm sorry, yeah, we're not looking this way, we're looking kind of that way. So in that case, RY is up, positive RZ is this way, and H is going to be located at the tippity top here. And our moment in the X is negative 750 inch-pounds. Negative means clockwise. it's going to look like this, which will, the equation for torsion, once again, is going to act in the xz plane because H is on the xz plane. Tau xz, or I mean, shear, is equal to the torque times rho, which is the distance to the, basically the radius, the distance to the point of interest, or to the outer fiber, to the outermost fiber, which is T times rho over J, J being the polar moment of inertia. So this is going to be equal to T times rho, or T times R, we'll switch the variable here, over J, which is the polar moment of inertia of a solid cylinder, is 1/2 pi r to the 4th. If you recognize pi r to the 4th, it's just half of the moment of inertia. This is going to be equal to that T, that torque is negative 750 inch-pounds. The radius is 1.5 over 2 inches over 1/2 pi times 1.5 over 2 to the 4th inches. This is equal to, let's find out. 1.5 over 2 times negative 750 divided by, we'll call it 0.5 times pi times 1.5 over 2 to the 4th. Bada bing, bada boom. Negative 1131.768 psi, pounds per square inch. Is the shear stress caused, this is shear stress, which is caused by the torsion, caused by the moment reaction in the X. So if we wanted to, we'll convert it to PSI later. Let's go ahead and move on to MY, the reaction moment in the Y, which is a moment acting on the non-longitudinal, on a lateral axis, is going to cause bending. So to analyze bending, once again, we look at the cut, the side of the cut. And for bending, we must look down the axis in which the moment is acting about. So MY is acting obviously in the Y. So we should look down the Y, which if we look down the Y, that means that H is going to be there. Z will be pointing upwards. RZ, RX. And what is the actual moment reaction in the Y? Minus 2250, which is, minus means clockwise, 2250 inch-pounds. So the equation for bending, bending, stress caused by bending, axial stress caused by bending. So sigma x is equal to positive m times y over I. But if you notice, y, this thing here is on the neutral axis. So y is going to be equal to 0, which is going to cause everything to be equal to 0. So the bending causes no stress because H is located on the neutral axis. Let's move on to MZ now, which is another lateral moment reaction, which will also cause bending. and we need to look down. To analyze it, we need to look down the axis in which the moment is about, which means looking down the z. If we do this, we should be looking down this way. By the way, this signifies, this here signifies the rest of the beam. If you haven't noticed by the different sign, the different axes. Here we go. So if we look down the z, that means here is ry, and here is rx, and h would be located right about here. So we're looking down the z axis. So rx, ry, and h is here. What is the actual moment reaction? 2,900 inch-pounds. Positive means counterclockwise. Boom. We'll call that 2,900 inch-pounds. And if you notice, the way I like to draw this is, so this will be like turning inwards counterclockwise. This will be like turning outwards counterclockwise. And our point of interest is at h, so if you notice, they'll go like that. So if you notice, h is in tension because of this motion here. The way the beam is actually bending is it is in tension. Therefore, tension means positive axial stress. Stress in the x is going to be positive m times y over I, which is equal to the moment 2,900 inch-pounds times here is the radius basically, or the distance between that and the neutral axis, between the neutral axis and the point of interest or outermost fiber in this case is 1.5. It's the radius, so 1.5 over 2 inches over I, which we discussed earlier. I for a, or the moment of inertia, sorry, for a cylinder is going to be pi over 4. Yeah, pi over 4 r to the 4th. Once again, over 4 times r, which is 1.5 over 2 to the 4th. This is going to equal, let's find out, 1.5 over 2. I should just be writing 0.75. Sorry, Dr. Lehman. This probably bugs you. It would be bugging me for sure, but here we go. Pi over 4 times 1.5 over 2. Once again, I should be doing 0.75. It's okay. It's all okay. Here we have our axial stress, which is 8,752 point, we'll call it 343 psi. And yes, that is accurate. So now that we've gone through the list and we found what kind of stresses the different loads cause, we can now combine them. So it'd be helpful to go through and highlight what we found. Sigma x, we found this. This is 0, it's irrelevant. Here, tau xy is this. Tau xy, once again, is here. Here on this page, sigma x, 56, okay, 0, okay. So we have them all. Let's go ahead and find them in our calculator and sum them up. So total axial stress in the x direction, we have here and here is all. So we just need to sum those together. So this plus the 56.588 that we found a long time ago. 56.588. So here's our total stress, axial stress in the X. 8808.931 psi, which is equal to 8.808.931 KSI. For tau xz, the total, we have two values here and here is all. So we need to sum these together. So this plus the 94.314 we found a long time ago. 94.314. Here she is. And we get a value of minus. I'm going to skip this step. We'll go straight to KSI minus 123. So 1.037, we'll call it KSI. Alrighty, so we will now jump to our state of stress to principal stress equation. It'll fit here. Sigma 1, sigma 2, or I'm sorry, our state of stress to principal stresses equation is equal to sigma x plus sigma z over 2 plus or minus the square root of sigma x minus sigma z over 2 squared plus tau xz squared. So which is equal to 8.0 whatever KSI. Call it 8.0, 8.809. 8.809. I'm going to use the float anyways. Plus 0 over 2 plus or minus the square root of so 8.809 minus 0 over 2 plus 1 or minus 1.037 squared. So something to note is that this is our tau max value. So we should calculate this first. So times 10 to the minus 3 to convert. I will also convert this value here times 10 to the minus 3. So now we're in KSI. So let's work with this. So this number squared plus, let me make sure this, let me make sure, times -1. Sometimes my calculator acts funny. Okay, cool. Negative, positive, it doesn't matter, get squared. So plus, we have this number here, our stress in the X, our axial stress, over 2 squared. And here we have it. So tau max is equal to 20.476 KSI. There's one of our answers. So now to get our principal stresses, we take our number, our axial stress in the X over 2. It's either going to be plus this value or minus this value. So let's do minus or plus first. Plus tau max. So sigma 1, our first principal stress, 24.88 That's fine. KSI. Yep. And then, like we said, if we have this value minus this value, because it's plus or minus, to find your principal stresses. Our second principal stress, sigma 2, is equal to minus 16.07. That's fine. KSI. And that is the end of the problem. I hope this was all captured. Yeah, it should be. And if I'm not, oh wow, okay. So I skipped a very important step. Good thing I noticed this before anyone yelled at me. Okay, we'll do it here. So when we combine and we get these values, we should definitely make drawings of the axes of our stress blocks. We should definitely make stress blocks to see which plane has the most stress. Good thing I noticed this. Sorry, Dr. Lehman, that you had to wait until now to see it, but here it is. Let's see. Why? So here are our stress blocks. Kind of late, but better late than never. So we have positive 8.808 or positive, whatever. I'll round it. Important thing is that it's positive, meaning it's in tension. And this is 8.809 KSI. And then we also have a negative XZ shear stress with the value negative 1.037 KSI. So negative means pointing this way because positive X goes this way, and then negative means goes this way with the Z because positive Z goes this way, and then just draw the other sides, and this has a value of 1.037 KSI. And we need to analyze the plane. We already did. We chose X and Z in our principal strain equation. The reason we chose this is because this plane here has the most stress acting on it. This one has none. This one has just the X stress, the axial stress. So this is why we chose the XZ plane to analyze the state of stress and find our principal stresses. And that makes for a complete solution to the problem. And that is it. Thank you.